This is a question from the online assessment, and you have been challenged to identify the target of a new compound. You don't know anything about this compound, but you know that it inhibits the growth of a methicillin-resistant strain of Staph aureus. So we're all trying to find new antibiotics or new compounds that will inhibit growth of these types of strains. Now you need to find the target, and the easiest way to do this is to use a process called multi-copy suppression. So this is a figure that was in the notes, and I just want to remind you how that works. So in this example, we've got E. coli, but we're going to put in our Staph aureus now. And when we add an inhibitor, it's going to affect something in the cell to inhibit the growth. And that's our goal. We're trying to find this target right there. So let's step back now and look at a technique that we can use to do that. We're going to start with that Staph aureus strain, this MRSA strain, and we're going to isolate chromosomal DNA. We're going to digest the DNA with restriction enzymes so we get lots of DNA fragments, because we're looking for the gene that encodes that protein target. We're now going to clone that into a plasmid. So we've got a plasmid, and of course the reality is that there are many copies of that plasmid, and each plasmid will get a different fragment of that chromosome. So let's say this is piece number 1 and this is piece number 2. Here's 1 and 2 up here. And by the way, this plasmid has ampicillin resistance on it. Now this is our library, because we're looking for the gene, as I said, that encodes this protein, and we have to kind of fish it out from the chromosome. We're going to put that library into the MRSA strain, and we are going to select all the AMP resistant cells, because that tells us that our library got into the cells. Now we're going to screen that whole library of AMP resistant Staph aureus in the presence of that compound. Now the important thing here is that we are using a high copy number plasmid, so anything that can grow now, we've got our MRSA plus the plasmid. And that plasmid gives us, maybe up to 300 copies of the plasmid per cell, and that means that if we are looking for the gene encoding this protein target, let's call it gene X, we've got 300 copies of gene X, and that's going to make 300 times as much of the protein target as a regular Staph aureus strain that doesn't have a plasmid. Now when we add the compound, it will still bind to the target, but we've now got so much of the target that the cells can live. So look down at this picture here. Here we've got excess target, we've got compound still inhibiting some of the protein, but we've got free protein that's uninhibited, and the cells can now grow. Well, here's another question from that assessment. You have a new plasmid that you've isolated from a strain called Shigella. And the plasmid is fairly large. It's naturally occurring. We've already seen that many of those are in excess of 100 kb. And you don't want to sequence the whole plasmid, so you're going to come up with a strategy to identify a fragment that contains just the origin. Now, the most straightforward way to do this is actually this method that was highlighted in your book. So again, this was precisely the example that they gave, in which we have a plasmid with an origin, and we're going to cut that plasmid with restriction enzymes that give us 1, 2, 3, 4, 5, 6 fragments in this case, but of course in reality you would probably have many more. And you're going to ligate that with a fragment that contains an antibiotic resistance determinant. When you ligate all these fragments together, some of them are going to be useless. They'll get the AMP gene, but they won't get an origin, so they will never even appear when you transform a strain that can replicate this plasmid. However, some of them will get both the AMP gene and the origin, and these will give rise to colonies. And you know that if it worked, you had to have obtained an origin because that's essential, and we take this colony, grow up these cells, and sequence the origin fragment that's on the plasmid. This question was looking at copy number differences between PET and puck vectors. Both of these are relaxed vectors, meaning that they are not coupled with the chromosome, but one is a very high copy number, puck, and the PET vector is actually only about 15 to 20 copies per cell. Both of them have nearly exactly the same origin. They have the PMD1 type coli1 origin, and the only difference is that the puck vector has 2 mutations in the origin that allow it to be replicated to a higher copy number than the PET vector.